So let's take a look here at how we might actually apply Rolle's theorem to a very specific question. Take a look here at example 1. Let's consider the function 5 minus 12x plus 3x squared, so a nice simple polynomial. And we're only going to consider it on the interval from 1 to 3. Now the first thing that I might want to do is to verify that the conditions or the hypotheses of Rolle's theorem are satisfied. And remember that there were ultimately going to be 3 of them. So let's go ahead and actually take a look at each one. So remember that the first one here was saying that my function had to be continuous on this closed interval. Well, that's definitely true because I have a polynomial and polynomials are continuous everywhere. So I can say here that f of x is continuous on 1 to 3 because it is a polynomial. Now the second condition required that on the open interval from 1 to 3, so not including these, putting parentheses on each edge, I needed to have my function be differentiable. Well, if I quickly think about taking the derivative of this function, I know that it would be minus 12 plus 6x. Very simple derivative here. But notice that the derivative then is also a polynomial. And in order, remember, to be differentiable, it just has to be the case that my derivative can be evaluated at all the points on the interval from 1 to 3. But since it's a polynomial, the derivative is a polynomial, then I should be able to plug in any number into it and always get an answer back. So notice here that I'll say that f of x is differentiable on the open interval from 1 to 3 because f prime of x is defined for all values on 1 to 3. And I know that again because it's a polynomial. The last thing that I have to check is to make sure that on this interval that this function starts and stops at the same height. So I'm going to have to check what is f of 1. So let's see, if I go and I plug in 1 here, I'm going to get 5 minus 12 plus 3. This is going to be 8 minus 12. This is negative 4. I'm also going to need to check what happens when I plug in the value of 3. So I'm going to get 5 minus 36 plus, let's see, this is going to be 3 squared is 9. 9 times 3 is 27. Notice here, though, this is going to be 32 if I add these together, and taking away 36 leaves me with minus 4. So yeah, it seems like since these values here are the same, that I have gone ahead and actually checked off conditions 1, 2, and 3. They are satisfied. So now I know that Rolle's theorem would guarantee me that there's got to be some value, there's got to be some input between 1 and 3 where I can get a tangent line of slope 0 on this graph. I'll write that here. Rolle's theorem tells us that there must be at least one point C in the interval from 1 to 3 such that, just a little abbreviation, f prime of C is going to be equal to 0. And in part B, I'm going to be asked to find all these values of C that actually do make this equal to 0. So notice to do that, I'm just going to go ahead and say, well, if I'm looking for when my derivative is going to spit out 0, then I can just say that, well, let's start by just calculating our derivative. We can see here that our derivative is going to be negative 12 plus 6x, and so it's no surprise that f prime of x is going to be equal to 0 whenever it's the case that negative 12 plus 6x is going to be equal to 0, and it's no surprise to find that that's the value of x being 2. So the only value of C which satisfies the conclusion of the theorem is 2. There it is. I found a value between 1 and 3 where it's the case that I get a tangent line of slope 0. Notice again, because if I plug 2 in for the value of x, I get that my first derivative turns into 0. So this is what Rolle's theorem allows us to actually do. We can find when our functions, or at least guarantee more specifically, that our functions will have a tangent line of slope 0 on this interval if we met the conditions.